at a polynomial. A polynomial is basically anything that's written like this: a n x to the n plus a n x to the n minus 1, blah, blah, blah. Basically, it's this. 3x to the 5th minus 2x to the 4th plus 3x squared plus 2. When we're going to learn how to factor that. Okay. That's basically what we're doing. Okay. Now, this is what you would call, in this case, what's the highest degree that you see? 5. So this would be considered a 5th degree polynomial. Okay. So whatever the highest degree is, that's our nth degree. Okay. The nth gives you the n value, the highest number of the exponent gives you what we call the nth degree. The number of terms that you can have in the actual polynomial then would be, if you think about it, its polynomials are written what we call you guys remember descending order? Or you guys would write polynomials as ascending or descending. Descending, I don't know why they taught you ascending, to be honest with you, because no one ever uses it, really. But descending would just be you go 5th degree, 4th degree, 3rd degree, 2nd degree, 1st degree, which is an x, and then your constant. So if you think about that, how many possible terms can you have if you have a 5th degree polynomial? 6. Okay. How many possible terms could you have if you have a 3rd degree polynomial? 4. What happens here is the number of terms in the polynomial. You guys understand what I mean by polynomial, by terms? What I mean by terms are these each individual pieces. These are terms within the polynomial. Each one of those in the polynomial are called monomials. Remember that? Oh, yeah. Okay. Polynomial is basically, monomials are a bunch of things put together with multiplication, if you want to go that route. So what you'll have is n plus 1 terms within the polynomial. Excuse me. And that's kind of all I want to leave it as for right now. We'll start to figure out the rest of these, what happens with the exponents as we go through this. There's a couple other little things that will show up, but for right now, I think we're okay just by knowing this much. Okay? Not terrible so far? This should be pseudo-remembering, because you guys did adding and subtracting the polynomials before, back in Algebra 1. You probably did a little bit of it. I think you did in circles, there was a couple of polynomials that get thrown together where you combine like terms, but other than that, geometry is such a weird thing. It has nothing to do with Algebra 1 or Algebra 2 except for the right triangle trick stuff. That's it. So a lot of schools are starting to switch sequencing of the math, where they're doing, instead of Algebra 1, Geometry, Algebra 2, Pre-Calc, and so on, they're doing what's called Math 1, Math 2, Math 3. I don't know if you've ever heard of that. Yeah, and that's the weird thing. There's so many different versions of it. It's tough to figure out how things are rolling. I understand the logic behind it, because it does kind of circle back to a lot of things all the way through, and it's not just, you're using everything you would use in Algebra 1, you're using all the way throughout all the different steps and stuff, and then as you get out Math 2, you're using all the stuff you would use in a sophomore level style thing and so on. So anyway, so what we're going to do is we're going to look at stuff like this, and let's see if we remember how to factor. For example, if I look at, and this looks a lot familiar from what we've been doing the past few days, the past couple of weeks. If I'm looking at 4x squared minus 24x, and I wanted to factor that, what would be the very first thing that I would have to do? Bring out a 4x. Okay, so if I bring out the 4x, bring this over, thinking, try that again. There it is. So what you're saying is, the first rule of factoring is to do what? GCF. GCF here is 4x. If I take that out, what am I left with? X minus 6. Okay. Is there an equal 0 here? So am I done? Yes. Okay. And those same exact rules are going to apply like we did. This was just a quadratic. Okay. The quadratic in this case had how many zeros? 2, what were they? If it was equal to 0, what would your two zeros be? 0, 6. Very good. Very good. All right. Now, if I go back to the other one, oops, let's try this again. If I go back to this was a little bit different. What did you have to do with this case? Well, yes, get a factor.
What is it called?
You multiply your tails, remember that? Okay. So you multiply your tails because there's no GCF. So what's 2 times negative 21? So we're looking to see what times what is negative 42. The add together to get positive 11. So you go through your factors. Okay. 42, we know it is 2 and 21. That combination doesn't get me to 11. Do you guys remember how to check to see if it's multipliable? Divisible. I knew the words are on there somewhere. Divisible by 3. What's 4 plus 2? Is that divisible by 3? Which means 42 is divisible by 3.
Is that only 1 with 3?
Yes. So 3 goes into 4 how many times? Once, how many are left over? 3 goes into 12 how many times? So that would be 3 times 14. Convenient. Okay. Now, if that middle term's got to be positive, which of those two has to be positive? 14. Good. So remember the little trick we did here. We had the 2x squared minus the 3x plus the 14x minus the 21. From here, we factored via grouping. Remember, this is going to be a style that you see whenever we had 4 terms in a sequence. This is still a polynomial. It just happens to have a repeated nth term, if you will. The x variable has the exponent of 1 twice. We split that into 4 pieces as opposed to just 3. Now, whenever you see 4 pieces, you always want to think, can I group it? What's your GCF? X. So we took out the x. You're left with 2x minus 3. What's the GCF of the next one? 7. So it was positive or negative? Positive. And then we have 14, 2x minus 3. Are those two things in the parentheses the same thing? Yes. Yes. So we write it down. And then you're left with the x plus 7. Remember, it's the x plus the 7, not the x minus the 3. There was somebody that did that. I don't remember if it was this one. Nope. What's 2 times 3? What's 3 times 2? Doesn't matter. Nope. Doesn't matter for the polynomial stuff when we do this either. Okay? So the little things here, all these little pieces of things that you have done still hold true when we get into the newer polynomial stuff. Only thing that happens with polynomials now is that it just takes an extra step or so. For example, one of the things that we've done in polynomials, let me get to a clean one here, are in quadratics, is that we learned how to do this. What was that called? Do you remember? That had a name. Difference of squares. We called it a difference of squares because is the first term a perfect square?
Yeah.
Is the last term a perfect square? Is that a subtraction symbol?
Yeah.
Yes. If you answered yes to all 3 of those, you knew that this was factorable to be between x minus 4, x plus 4. Right? I hope. Okay. Now,
Difference of triangles.
not triangles. What is the third degree? What is that called? Cube. It's a difference of cubes. So this also works. Was this factorable? Was that factorable?
No.
Why wasn't it factorable?
There's an addition.
It's the addition sign. Remember when you had difference of squares, if you answered yes to all 3 questions, you were good. The moment you said no, and the no was, is that a subtraction symbol, you would stop. We can still find the zeros of that, they're just imaginary. Okay? But we can't factor it. Right? But what happens here, cubed is what, 125? Yes. That can work. There are what we call sums and differences of cubes. You're going to be able to factor these, and there's a special pattern. Know how we would always ask the question about the difference of squares? It was x, plus minus the square root of either side. With these guys, there's special patterns. For example, actually, I'll just show you the rule, and we'll come back to these. There are two rules here. We have what's called the sum of cubes and the difference of cubes. They're relatively straightforward. There is a little shortcut you'll notice as you're going through it. So if I'm looking at the sum of cubes, I'm going to ask, is the first term a perfect cube? Is the last term a perfect cube? Do you know how to check to see if that works in the calculator? Guess how to do a cube root? That's cubing. The caret will get you the cube. That's fine, but there is a cube root button on here. So if you go to, I want to say it's alpha window.
Yeah. Oh yeah, it's right there.
Alpha window 6 gives you what's called an x root. You just have to change that to a 3. Or another way of doing it is if you hit math option 4. Math option 4 will get you to the cube root as well, and that'll work. Okay. Math option 4 is probably a little bit quicker. And go from there. So you do math 4, and if I want to figure, and I want to do 125, it'll tell me what it is. Okay. That's how you check it. Math 4 is the quickest way of doing it for setting those things up. Okay. So what happens here is the special pattern. If you look at the rules, if you look at the rules, there's something that happens here. If you have it's the sum of cubes, first term's cube plus the second term's cube, the first thing that comes out is the cube root of both of them. So if we had the example a second ago of, what was it, x to the third plus 8.
Yeah.
So what's the cube root of x cubed? X. It was x. What's the cube root of 8? 2. So you take basically the cube root of both of these, and they go here. All right? So the first would just be a plus b, whatever your cube roots are. And then you get to a trinomial. The trinomial for both of these will always look the same. A squared, and then the end is plus b squared. In the middle is an ab. What changes is the sign of the middle term of the trinomial. If this is a plus for sum, the trinomial has a minus. Notice how the difference of cubes goes minus plus plus. The sum goes plus minus plus. The first two, the first one is always the same sign as what it is. The last one is always positive. First one is always the same sign. The last one is always positive. The middle sign is always the opposite of whatever you're dealing with. Okay? All the other square values and stuff hold true. So again, if this is my a, this is my b, I write x squared minus a times b, and then I square with 2. Whenever you are factoring a sum or a difference of cubes, you're going to get one real 0 and non-factorable ones. Okay? And we go from there. That's how these things look. It's a special pattern that you haven't dealt with before, but the more we practice it, the more we go through them, the easier it becomes. Again, if you have, I do 27x cubed. 27 is 3 cubed, right? 3 times 3 times, yeah. And then I do minus a 125. All right. The easiest thing to remember here is that I take the cube root of this, So the cube root of 27 is 3. The cube root of chunk cubed is chunk, so there's the x. So you get 3x minus, well, cube root of 125, I think we just said it, was 5. Again, notice, it's the same sign as I start with. In the trinomial, then, it's this first term squared. So what's 3x quantity squared? 9x squared, yeah. All right. The next one is going to be the opposite sign of a negative. Bless you. Opposite of a negative is positive. What's 3x times 5? 15x. And then the last one is always a plus, and then it's that last value squared. What's 5 squared? 25. And you're done. Okay? That's what that's going to look like. It's not that difficult. It's just getting used to that special pattern. And once you do a few of those, you'll be like, oh, okay. All right? Then we just go from there. Not so terrible, I hope. So, let's look at this. I'll write it the next. 16x to the 5th minus 250x squared. Now, it's just two terms, right? It's two terms. It's got subtraction in between it. But no matter what is always your first step? GCF. Okay. So when I'm looking for a GCF here, obviously you guys okay that an x squared, they both share that? Okay. So we know that an x squared can come out. So I'll have an x cubed minus something. But I have to figure out, is my GCF going to be a 16, a 4, an 8, or a 2? So if you try 4, real easy. Does 4 go into 25? It does, but you have just the 1 left over, and 4 doesn't go into 10. Does 8 work? I mean, if 4 doesn't work, then 8's not going to work, right? So that means the only thing that's going to work is going to be 2. Plus, one of the other dead giveaways is, now that you're learning something about cubes, this is pretty close to a cube root. What do I have to take out to get to a cube root? 2. So you have 8x cubed minus the 125. All right. So, is there anything here equal to 0? If I'm just factoring, that 2x squared has to come along for the ride every time all the way through, okay? So we finish it out. So we go through the special patterns. Again, is the first term a perfect cube? Is the last term a perfect cube? This time it's a subtraction. So we have to go through the special pattern. So this stays the same, so it's 2x squared. What's the cube root of 8x cubed? 2x, very good. Do I keep the same sign or do I change it? What was the rule, remember? Keep it. Yep. Keep it. And then the cube root of 125? 5. And to be honest with you guys, they don't get really crazy on the numbers on these things. It's 125s, it's 8s, 27s. Every once in a while you might see an 81 where you can take some of it out, and take a 3 out and get to the 27, things like that. They're going to be workable. Okay, it's going to be very, very workable. So now, in the trinomial, your first term is the 2x squared. So when I square 2x, remember you're squaring the whole thing, so you get 4x squared, good. The next one, I change my sign, and I multiply these two together, and you get 10x. The second sign is always the opposite of whatever this one is, no matter what. If this was a plus, this would be a minus. And then the last one is always positive. Okay. So if you want to think,
even though the sign is
yes, because you're looking at this as the a value here. The a is 2x. The b is 5. Okay. So the pattern that works here is always going to be this: same, change, plus for either one of them. Same, change it, plus. All right, will always work. And then the last thing would be 25. And that's factored form. And that would be factored form. Yay! Sums and differences. It's some different.
Oh, really?
Whatever. I try. Hey, how many terms are here? There's 4, which means we should probably try and do what? Group. Anytime you see 4, always try to factor by grouping. Okay, anytime you see 4 terms, always try to GCF and factor via grouping. So if I have x cubed minus 2x minus 9x plus 18, if I group these, what's my GCF for the first 2 terms? X squared, very good. If I take out the x squared, what am I left with? X minus 2, very good, very good. Now, what was my rule here whenever my third term was positive? Good, plus the negative before you group it. The reason that I always want you guys to do that is so that when you don't forget to take the negative back out with you. Okay? So there, excuse me, what's my GCF now? The 9 and the 18. The 9, but I would take out the negative 9. What are you left with in the parentheses? Hey, are those 2 things in the parentheses the same thing? Wow. Oh, look at that. Convenient, isn't it? So you have x minus 2, and then you have, oh, look at that, x squared minus 9. Hey, isn't that factorable? The difference of squares, isn't it?
Oh, yeah.
It is. Is that a perfect square?
Yes.
Is that a perfect square?
Yeah.
Is that a subtraction symbol?
Yeah.
You can factor it further. Okay? You're going to see difference of squares hiding within. You might even see difference of squares within differences of squares, which is a possibility. Okay? You're going, let me show you. What if I do this? Is the 4th a perfect square?
Yeah.
Is 16 a perfect square? So if I factored that, it's a difference of squares. That would give me, well, x squared, because x squared times x squared becomes x to the 4th, doesn't it? Remember how when you multiply, you add your exponents? All right. What's the square root of 16? 4. For which one? Can I do anything with the x plus 4? No. So then you keep the same thing, x squared plus 4, and then x minus 2, x plus 2. It is still factorable when you have higher degree polynomials. You just keep breaking it down further and further. You get to a point where you can stop when you get to the x squared plus 4, because that's no longer factorable because you've got imaginary zeros. We'll talk about when we get to solving these things, what we're going to do with that probably a little bit tomorrow. Okay? How do we solve these things and plot them? Because then on Friday, we're going to show how they behave at the ends, at the tails. So we can learn how to start rough sketching higher degree polynomials. Because, as remember, quadratics are either up like a cup or down like a frown. Polynomials have many different degrees, but there's only certain ways that they're going to end up. What I mean by the tails, at the very ends of the graphs. And we're going to figure out ways to do that along the lines of plotting zeros. And all meshes together as we go. Try that. Actually, when you write this out, just don't worry about the equal 0. Just write it like that. I don't want to do the equal 0 stuff today. I just want to do the factoring. Okay, I just want to do factoring. and that's why we go through these questions. Is that a perfect square? Is that one a perfect square? Is it subtraction? I'll say no to any of the
Square minus 12.
Notice how this is written in descending order. Try to make sure you put things in descending order. It does help keep things clean. Every once in a while, they'll throw something in a different order on you just to harass you. I don't think it's that scary. I mean, it's not like it's raining. She can hear me. She's ignoring me now. She's used to it. I'm hoping you got that far. Good. Good. What was your GCF in the first group? X squared. Okay. Then 3x plus 7.
I like it.
What'd you take out of the next one? -4. Good. I like that. And you got 3x plus 7. Hey, look at that. Two terms are the same, aren't they? Did you guys know that when I ask you this question, are these two terms the same? You're just taking the GCF out. You know that? You're just doing another GCF. We just don't say that. And then can you go any further? Yep. So your final answer would have been x minus 2, x plus 2.
Yeah.
Does it matter the order in which any of these go? No. Does not matter whatsoever. Does not matter whatsoever. One of the things you can always do to see if you did this correct, you could FOIL all of that out. Or what do you know that your constant has to equal? What does your constant have to equal here? -28. Now that -28 is also going to represent what on the graph?
Y-intercept.
Very good. It's going to be your y-intercept. So one of the things you can do, I always tell students to look at this. If you take your constants, however many there are, and multiply them together, you should get -28. What? What's 7 times -2?
Oh my God.
What's -14 times +2?
And then,
So, do you agree that's the constant? So, when you have, Sarah was just asking this question, when you graph something, your y-intercept occurs when x is 0. What's 0 cubed?
Oh,
What's 0 times 3? What's 0 squared? What's 0 times 7? What's 0 plus 0? What's 0 times 12? What's 0 plus 0? What's 0 minus 28? There's your y-intercept. Your constant, your last value, whatever that is always your y-intercept. No matter what kind of polynomial it is, whether it's quadratic or linear. Mx plus b, your b was your y-intercept. Because if x was 0, there's your y-intercept. Cover and solve, why we did intercepts. Okay? Just little tips. Right? Yep, but because also remember what you can do here is if I rewrote this out, do you agree that this one is x squared minus 4? If you FOIL that, you get 3x cubed minus 12x plus 7x squared minus 28. Change the order around, there's your 7x squared minus 12x. And it FOILs itself back up. All right. Try those two real quick. Your roots. Is 4 divisible by 2? And it's a perfect cube. It can be both. you can square root. Think of it this way. When you take a square root, you're using what's called a half power. Alright. Bless you. We get into more of that technical stuff later, but it's how roots work. So, what are two numbers that are the exact same that you multiply together to get 81x to the fourth? It has to be 9x squared. Think of it that way. So you have a 9x squared, and then what's the square root of 16? 4. And then it's going to be 9x squared plus 4. It's still a difference of squares, but within that difference of squares, only one more of those are factorable. The one with the subtraction symbol. So here you wind up with a 3x minus 2, 3x plus 2, and then the 9x squared plus 4. And then you leave it, because you can't factor a sum of squares. Yeah, there isn't a way to do that. Now, eventually we'll talk about finding all of those zeros and why one of those is why two of those are imaginary and two of those are real. Because when we learn about how do you graph these things, it explains kind of why this is happening. Okay? So this is why, if you notice, we're starting at 6-4. I'm starting by working with you guys on stuff that we just basically got done doing, all that factoring, and then I'm going to switch it to tie it to why the graphs work. So I thought about doing something different. So hopefully this works. If it doesn't work, I won't do this next year. Yeah.
Wait, so I think he's not doing this year?
Because I wanted to try it. You guys can be my guinea pigs. Or the proverbial, what was the monkey's name that went up in the...
Curious George.
Curious George. You're right. It's Cheers, George.
That movie is so good.
My kids used to watch that all the time, and it drove me nuts. Anyway,
We should watch
first rule of factoring is to do what?
it.
GCF. In this case, there's a GCF. I have a 4x squared. Now I'm left with x to the fourth, because x squared times x to the fourth will give you x to the sixth. Remember, you're just subtracting the exponents as you're factoring things out. Okay. This gives you minus 5x squared and then plus the 6. Are we okay with me on that?
Yeah.
All right. Now, that's a trinomial, isn't it?
Yeah.
Now, it's a trinomial with what degree? It's a fourth degree trinomial, but there's only 3 terms in it. A fourth degree polynomial could have up to 5. What's happening here is that there's 2 placeholders. There's 0x cubed, and there's a 0 times x. They just don't write it. Okay? Now, what happens here is when you have a trinomial, just the 3 terms, and your exponents go 4, 2, and then nothing, factor it exactly like you would a regular quadratic. What times what is positive 6 you add together to get 5? Negative. Negative 3, negative 2. What times what's positive 6 get negative 5? So the two numbers are negative. So negative 3, negative 2. All right. Yeah. So this 4x squared still goes along for the ride. Now,
And so should be like X.
exactly. The first term becomes x squared now, and then it's just, excuse me, x squared minus 2, x squared minus 3. Because if you FOILed all of that out, x squared times x squared is x to the 4th. X squared times negative 3 is negative 3x squared. Negative 2x squared gives me my middle. And now, is this a perfect square? Is that a perfect square? 2 is not a perfect square, so I can't factor this any further. Is x squared a perfect square? Is 3 a perfect square? And then I can't factor it any further.
So, you got a really good relationship, like how you can factor like a like
It works because it's being cut in half. If it goes 4, 2, nothing, you're good. If it goes...
So, like, 8 or nothing, is that one?
Yes, because what's 4 plus 4? Whenever you're multiplying exponents, multiplying things together with exponents, you're adding your exponents. So if the two exponents can add up like 3, if it goes 6, 3, nothing, you're good. If it's 8, 4, nothing, you're good. You treat it the exact same way. Okay? That's how this works. Let's see what I have. That. Now, I don't know if these are the ones I want to. Let me grab my book here real quick. I don't think this sounds right. I want to make sure I didn't put in here anything with zeros. Hello. Yes, sir.
I assume that this is.
It is. They did it and caught it.
Okay. Just making some rounds just to make sure.
Yep.
So, all right.
Very well. Yep, no problem. Those will work. Straight factoring, go by threes. PDF files on the calendar right now. I'll add those numbers on there. It's all factoring, and some more factoring. Okay? You want to take a picture of the book? The book's right here as well. Yes, ma'am. Okay. So when you do those,
19 is taken.
19
is taken.
We took out the 4x squared. You're okay with that? Oops, jeez. Just get out of the way. All right, you okay with this? Move back here.
Yeah.
I'm going to do something called use substitution. All right? Now, if I let u equal x squared, this is x squared squared. Okay? So that would be u squared minus 5u plus 6. What times what is 6? You guys got to get negative. So you have u minus 3, u minus 2. What was u equal to? Anytime your powers go down, that's goes down in half like that. That's why sometimes. That's why I want to do it, because sometimes when I show this little use substitution trick, a lot of people will see it right away. Treat it like you would normally. When you have a trinomial, try to treat it like you have it normally. Square. Imaginary zeros, we're not finding those yet. Imaginary zeros are when you have x squared equals negative 4.
Oh, it would just be that.
So you x equals plus or minus.
Oh, okay. I know how to get that.
Imaginary zeros is when you had it where, let's say it was x squared plus 3. These zeros are going to be at plus or minus 5 or that's what that would be. No problem.
Jeez.
My strategies have not been where I